Hello and welcome. Today we are going to discuss hybridization of carbon atoms. Carbon shows three types of hybridization, which is sp3, sp2 and sp. We are going to learn what are these and how they affect the geometry and the reactions of any organic compound. Let's start with first discussing what is hybridization. So hybridization is a concept. Like many other concepts in organic chemistry, it is also a concept that we use to explain our observations about structures of compounds or the geometry of the compound. The concept of hybridization is linked closely to the orbital theory, which states that the electrons live in orbitals. Okay, and each orbital can hold 2 electrons. Okay, now there are various kinds of what we call subshells, which are groups of these orbitals. For example, we have the s subshell, which contains one orbital. We have the p subshell, which contains the 3 orbitals, and we name them as px, py and pz. Similarly, we have the d subshell, f subshell and so on. For our purpose, we will limit ourselves to the s and p subshell. Now for carbon, which contains 6 electrons, these electrons live inside the s and the p subshell, and this is how we write the electronic configuration for carbon. We start with the first s subshell and give it 2 electrons. Then we move to the second s subshell and give it 2 more electrons, and then the remaining 2 electrons go inside the p subshell. If we draw the diagram for this, we have 2 electrons here in the 1s subshell, then we have 2 more electrons in the 2s subshell, and then 2 electrons in the 2p subshell. We call this the ground state for carbon. However, whenever carbon tries to form bonds, it first enters what is called the excited substate. And in the excited state, this arrangement changes a little. The 1s remains as it is. One of the electrons from the 2s subshell moves to the 2p subshell, and this pair also separates. So what we have is this representation. Now you can see that there are 4 places where electrons are unpaired. 1, 2, 3, 4, and therefore carbon forms 4 bonds. Okay. This is what the orbital theory explains. Now we have still not reached the place where hybridization comes in. Before that, let's take an example. This is the formula for methane. We have 1 carbon atom and 4 hydrogen atoms. So if we draw this, there are 4 bonds between carbon and hydrogen. Now we saw the excited state for carbon, in which there was 1 electron unpaired in the 2s subshell and 3 unpaired electrons in the p subshell. Suppose hydrogen comes in to form bonds with carbon. So we can get one electron from hydrogen for pairing with the 2s subshell electron. We can also get one electron from hydrogen for each of these p subshell orbitals. Hydrogen's electrons live in the 1s orbital. So in that case, we can see that this bond is going to be formed between S and S, whereas these three bonds are going to be formed between S and P. So these bonds should be different, right? And that's where hybridization comes in. Experimentally or through analysis, scientists found out that each of these bonds are identical. They are not different from each other. That means that something else must be going on, because otherwise we should have one S-S bond and three sp bond, and they should differ from each other in bond length and their energy levels, etc. But what we find is all the four bonds of hydrogen and carbon in methane are identical. The orbital theory does not explain this. And so in comes hybridization. What hybridization states is that before bond is formed, the carbon atom, which has 4 electrons, 1 in the s subshell and 3 in the p subshell, these orbitals undergo a mixing, and the result of this mixture are new hybrid orbitals which are identical to each other in energy and therefore in bond length, and we call these orbitals degenerate orbitals. Degenerate means with the same energy level. Now suppose we have one s orbital combining with 3 p orbitals. Then how many orbitals are we putting in as input? 4. And that will result in 4 output orbitals, and they will be of the type sp3. The 3 and the 1 here, which we have not shown, indicate that one s orbital has combined with 3 p orbitals. This is what we see in the case of methane. Okay. Similarly, if you take one s orbital and 2 p orbitals, then the input is 3. So after the mixing, we will get 3 hybrid orbitals, and they will be sp2, meaning we take one s orbital and 2 p orbitals. This is just a way to name these orbitals. sp2 is a name. Now what if I take one s and 1 p orbital? So our input is 2, and therefore this mixing machine will give us 2 orbitals that are of the sp type. Once again, sp is the name given to these hybrid orbitals. So if we look at the properties of these orbitals together, we have sp3, we have sp2, and we have sp. These are the possible cases for carbon. One of the things that is asked in this cases is the percentage S character. That's very simple to calculate. Here in sp3 we have 4 input items and one of them is S. So we will take 1 by 4 into 100, which is equal to 25%. What will be the percentage S character in sp2? We have 3 different kinds of orbitals and one of them is S. So 1 upon 3 into 100, which is 33.3%. And in the case of sp, we have two orbitals out of which one is s, so it will be 1 by 2 into 100, and that comes out to be 50%. What is the importance of this percentage s character? This percentage s character tells us about the acidity. More the percentage s, more is the acidity. So alkynes are more acidic than alkenes, which are more acidic than alkanes. The next part is the geometry. For sp3, we have a tetrahedral shape with a bond angle of 109.5 degrees. For sp2, the shape is planar and specifically a trigonal shape, and the bond angle is 120 degrees. And for sp, it is a linear shape and angle is 180 degree. Hybrid orbitals only form sigma bond. There is another kind of bond you will see, which is the pi bond, which is formed by those orbitals that do not take part in hybridization. In the case of sp3, all the 4 orbitals, 1 from s and 3 from p, took part in hybridization. So for the carbon, that is sp3, you will see only sigma bonds. So it will be 4 sigma bonds. Any carbon that is sp3 will have 4 sigma bonds. In the case of sp2, only 3 orbitals, 1 from s and 2 from p, took part in the hybridization. So there is one p orbital that is left, and that p orbital can form pi bonds. Okay, so in these cases you will see 3 sigma bonds and 1 pi bond, which comes from the p orbital that did not take part in hybridization. Similarly, for sp case, only 2 orbitals took part in hybridization, so there will be only 2 sigma bonds here, and the remaining 2 bonds will be pi bonds. Now this can be either C triple bond C, so both of these are sp, or it can also be C double bond C double bond C, in which case these carbon atoms at the ends have only one double bond, so they will be sp2, and this carbon atom in the middle has 2 double bonds, so it will be sp. So let's move to the main part of this video, which is how to identify the sp, sp3 and sp2 hybrid carbons. All 4 sigma bonds, or other way to see it is 0 pi bond, then the hybridization is sp3. If 1 pi bond is present, then the hybridization is sp2, and if 2 pi bonds are present on a carbon, then the hybridization will be sp. This is the rule that we will use to figure out the hybridization of each of the carbon atoms. Now let's see the structure of methane. There are only sigma bonds present here. So this is going to be an sp3 hybrid carbon. Okay, so all of these bonds are between the s orbital of hydrogen and the sp3 hybrid orbital of carbon. CH3, CH3, which is the ethane molecule. Both of these carbons have only sigma bonds, so they are sp3 hybrid carbons. What if we have CH3, CH double bond, CH2? Now in this case, the corner carbon atom has only sigma bonds. There is no pi bond here. So this is sp3. But this carbon atom has one pi bond. So it will be sp2. And similarly, this carbon atom at the end also has one pi bond. So it will be sp2. Easy, right? What if we have CH3, C triple bond, CH? In this case, again, the leftmost carbon atom has no pi bonds. So that is sp3. The other two carbon atoms have two pi bonds. The first bond here is a sigma bond. This bond is a sigma bond, and the remaining two bonds are pi bonds. So there are two pi bonds here. So this will be sp hybrid carbon, and this will also be an sp hybrid carbon. Okay, that's how easy it is to figure out the hybridization of carbon atoms in any molecule. Let's look at another example. Let's decide the hybridization of each of the carbon atoms present here. Starting from, say, here. Can you see a pi bond? Yes, there is one pi bond. So this is sp2. What about this carbon? Again, there is a pi bond. So it is sp2. For this carbon atom, we see one pi bond. So this is also sp2. This one is also sp2. Come here. This carbon also has a pi bond, so it is sp2. And this carbon atom also has one pi bond, so it is also sp2. All the carbon atoms in a benzene ring are sp2 hybrid carbon atoms. What about this carbon atom? It has two pi bonds, so it's an sp hybrid carbon. This carbon also is sp hybrid. Now look at this last carbon atom. It is interesting because there is a double bond present, but that double bond is with the oxygen atom. Do we consider that when finding the hybridization or not? Well, the only thing that matters is that there is a pi bond or not. Is there a pi bond? Yes. So this will be sp2 hybrid carbon. It does not matter to which atom this pi bond is attached. Now if I ask you, what is the number of sp2 carbons here? Can you not just count and tell me that there are 1, 2, 3, 4, 5, 6, 7 sp2 carbon atoms? So the answer for this is, now a lot of interesting questions can be framed using these concepts. For example, I can ask you the number of sp2 sigma bonds between carbon atoms. Can you count that and tell me the answer? We look at the carbon-carbon bonds. Let's start from here. This bond is between a sp2 and sp2 carbon atom, so this counts. We have another such bond here, so we have 2 sigma bonds so far. Then the third one is here. It is also between sp2 and sp2 carbon atoms. Let's keep on counting. We have fourth bond, which is also between sp2 and sp2 carbon. What about this bond? This also is between an sp2 and sp2 carbon atom, and this sixth one here is also between an sp2 and sp2 carbon atoms. Do we have more? What about this bond? It is between an sp2 and an sp carbon atom, so this does not count. This sigma bond here is also between an sp and sp carbon atom, so does not count for us. Similarly, this bond here is between an sp and sp2 carbon atom, so it does not count. And this bond here is between an sp2 carbon but an oxygen atom, which is not asked in the question. So we can see that we have 6 such bonds available in this compound. You can also be asked the number of pi bonds. It's easy to see that there is a pi bond here, then a second pi bond here, and a third pi bond here, 3. Then we have 2 pi bonds here, so 5, and another pi bond here. So we have a total of 6 pi bonds. So this is how you can read the structure and identify the hybridization of carbon atoms, the number of sigma bonds, the number of pi bonds, the number of sp2 or sp bonds, and a lot of questions can be framed on this. Go ahead and do lots of practice on this concept, and I will see you in another video.